In this lesson, we're going to talk about precipitation and predicting products. Sometimes when you mix two solutions, a solid substance falls out or precipitates out of the solution mixture and ends up at the bottom of the reaction vessel. Just like rain precipitates out of the sky, the solid can precipitate out of a solution. Here's an example. When you mix barium nitrate and potassium chromate, the two of them initially dissolve just fine together. One of them's a colorless solution, and one of them's a yellowish solution. When you mix, you see a cloud form, and if you let the cloud settle, you'd see the solid yellowish substance at the bottom that is barium chromate. We try to diagram this. Which substance has settled to the bottom of the beaker? Which ions are still floating in solution? Well, if the red spheres are potassium and the purple spheres are barium, and the 1 blue and 3 red together are nitrate ion, and the 1 yellow and 4 red are chromate ion, we can see what ends up at the bottom is barium paired with chromate. And what's floating around in solution at the end is the potassium ions and the nitrate ions. We can represent this reaction thus. K2CrO4, that's potassium chromate. We put an AQ after it, meaning it's aqueous. It's dissolved. Barium nitrate, BaNO3 in parentheses and then a 2. We put the AQ after that one because both solutions were initially completely dissolved. There was no solid initially. But then when you mix them, barium chromate, we put with an S after it because it's the solid. It's the thing that falls out of solution. It's the precipitate. And 2KNO3, potassium nitrate, remains aqueous. So the ions floating around at the end are the potassium ions and the nitrate ions. And those are part of the potassium nitrate product. AQ stands for aqueous. Those are the substances still dissolved. S stands for solid. That's the precipitate. Some other terms that are important. When we say solubility, we're talking about the ability of a substance to dissolve. So if it's highly soluble, it's highly able to dissolve. If it's not soluble, or sometimes we'll use the word insoluble, it means it's not able to dissolve. Soluble means able to dissolve. It's the aqueous substance. This would be the thing floating around in solution even after the reaction has occurred. And if it's soluble, the state of matter is given an AQ, meaning aqueous, meaning it is dissolved even after a reaction has occurred. Insoluble, in meaning the negative prefix, the opposite of what comes after it. Not able to dissolve. This is the solid precipitate. This would be the thing sitting at the bottom of a reaction vessel after the reaction has occurred. And we give it the state of matter designation S, meaning it's solid. Now, unfortunately, in my mind, the word solid sounds a little bit like soluble, but they mean exactly the opposite. The soluble substance is the thing that's aqueous and is therefore not a solid. The solid is the thing that's insoluble. Try to keep that straight. I wish those words didn't sound so similar. When we're asked to predict products in a chemical equation, the first thing we need to do is look at the formulas. We're always going to be dealing with ionic compounds when we consider potential precipitations. Identify and list out the ions that make up the reactants. Watch for polyatomic ions. That means you've got to know your list of polyatomics. Have it out if that's helpful. Note which ions are positive and which are negative. The positive ion will always be the first one listed in a chemical formula, and the negative ion will always be the second one listed. And remember, ionic compounds always consist of a positive ion paired with a negative ion because it's got to be neutral overall. Second, write proper formulas for the products. The products will be the new combinations of ions. The reactants have a certain way of combining a positive with a negative ion. The products will be the other way that you can combine positive with negative. Positive ions still always pair with negative ions. Never put two negatives together. Never put two positives together. They would repel each other. Lastly, write the full balanced equation, keeping in mind the coefficients needing to balance the number of atoms of both sides. And then lastly, write AQ after the substances that are still dissolved. Write S after the precipitate. If there is one, there might not be a precipitate. You'll have to consider a list of what we call solubility rules. Ooh. Let's take a look at an example. Let's say we're asked to write the balanced equation for the reaction that happens when sodium solutions of silver nitrate and potassium chloride are mixed. Silver nitrate, AgNO3, and potassium chloride. Let's identify the positive and the negative ions. Remember, the positive ion is always the one listed first. So in the formula AgNO3, the first substance listed is the Ag. That's silver ion. I know from my previous study of the periodic table that Ag is one of those special elements in the transition metal block that has a stable charge. And of course, I memorized it back in first semester. It's a +1 charge. The other compound has K listed as the first element. Potassium, that's in column 1, and I know that elements in column 1 take a +1 charge. So our positive ions are Ag +1 and K +1. It's important to be able to identify those. The other ions, and I color-coded them blue in the notes here, NO3-, that's one of your polyatomics, nitrate ion. And Cl, you can find Cl in group 17 on your periodic table. That's the column that takes a -1 charge. So those are our ions, and it's important to keep that straight. Before reacting, the Ag was paired with NO3, and the K was paired with Cl. But what are the new ways of combining a positive ion with a negative ion? We always need to think about new ways to pair up. If Ag was initially paired with NO3 and K was initially paired with Cl-, the new combinations of ions would be Ag with Cl- and K with NO3-. Thus, if we were to write good formulas for those products, we would have AgCl and KNO3. Remember, an ionic compound is neutral overall. The total positive charge has to cancel out the total negative charge. That's why one atom each of Ag and Cl makes a neutral compound, because the size of their charges are both 1. And similarly with K and NO3, the K is a +1, the NO3 is a -1, so one ion of potassium cancels out the charge of one nitrate ion. Also remember, when writing formulas for products, list the positive ion first. So it's not NO3K, it's KNO3. It's not CLAG, it's always AgCl, positive ion first. Thus, we write our balanced equation out. We would write AgNO3 plus KCl yields AgCl plus KNO3. If this equation were not balanced, at this point, you would look and add coefficients. Turns out that this equation is balanced as written, so you don't need to do any more with the balancing. But there is something left to do, and that's to consider which of the products, and it's only going to be a product because initially the two solutions were dissolved, but potentially one of the products is a solid. In this case, it's AgCl. Now, I wouldn't expect you to know that ahead of time. Here's a way of picturing what we've got. Ag and NO3, K and Cl, all aqueous initially. But at the end, we've got K and NO3 remaining aqueous. And at the bottom of the reaction vessel, Ag and Cl. one of those product compounds does not dissolve. It precipitates. How would you know which is which? Well, shortly, I'm going to give you a list of rules to apply to figure that out. But first, I'd like to do a sample problem with you. Or actually, let me give you that list first, and then we'll do the sample problem. How would you know which substance stays dissolved and which will precipitate, if any? Because it's not necessarily going to be a precipitate. You could sit there and observe the mixing of several thousands of different solutions and then thereby develop a list of solubility trends. And one of the labs that I'd like to do with you, called Mission Insoluble, is going to have us do this very thing. We're going to mix several different solutions and try to figure out what's the most soluble, what's the least soluble. Or you could trust us when we give you a list. There are solubility trends developed by other scientists that are very, very reliable. This list of solubility rules you will have access to for all tests and quizzes in my class. So you do not need to memorize it. However, you do need to know how to use it. And you do need to have at least some familiarity with it. So let's give these rules. They are written in order of importance. Rule 1, and by the way, these are solubility rules for ionic compounds only. You should assume that anything that's covalent, if you were to come across it, would be soluble. That means able to dissolve. So for ionic compounds, rule 1, nitrate salts are soluble. 2, salts that contain group 1 metals or ammonium ion are soluble. Oh, what are group 1 metals? Students, remember back to the periodic table. When we say group, we're referring to a vertical column. So elements in column 1 that are metals, so hydrogen's not one of those. A group 1 metal or ammonium ion would make it soluble. Rule 3, salts that contain chloride ion, bromide ion, or iodide ion are soluble, but there are some exceptions, except when combined with silver ion, lead 2 ion, or mercury 1 ion. Rule 4, salts with sulfate ion are soluble except for these specific examples: barium sulfate, lead 2 sulfate, mercury 1 sulfate, and calcium sulfate. Rule 5, salts that contain hydroxide ion are not soluble. They're insoluble. And rule 6, this is the last one, salts that contain sulfide ion, carbonate ion, chromate ion, or phosphate ion are also not soluble. Again, students, you do not need to memorize this list of rules, but you do need to know how to apply them. Sometimes you'll encounter a substance that has 2 or more rules that apply to it, and sometimes those rules conflict. If that's the case, whichever rule is listed higher in this list would be the one that takes precedence over the other one. Let's try a problem together. We're going to be asked to write the balanced chemical equation for the reaction that occurs when the following solutions are combined. And we're going to color code positive ions red and negative ions blue. AgNO3 and LiBr. First, let's list out the positive ions. Remember, the positive ions are the ones listed first in the formula. So I know that Li is lithium ion. Lithium's in column 1 on the periodic table. Elements in column 1 will take a +1 charge. The other positive ion is Ag. Now, Ag is one of those special elements in the transition metal block that have a stable charge. There's 3 that you need to have memorized, and Ag is one of them. It's a +1 charge. Next, let's list out the negative ions. One of the polyatomic ions is here, and they even give you this note in parentheses. Nitrate ion is NO3 minus. That's one of our negatives. The other negative is Br. Try finding Br on the periodic table. Column 17. That's going to take the -1 charge. Okay, so we have our positive ions and negative ions. Initially, Ag was paired with NO3, and Li was initially paired with Br. The new way of combining a positive with a negative ion would be Li paired with NO3 and Ag paired with Br minus. If you combine Li and NO3, notice that their charges both have a magnitude of 1. So if you were to crisscross these charges, you would come up with the formula Li1 NO3. And if you had put parentheses around the NO3 and a 1 outside it, it would be fine. It's just that if there's a subscript 1, you typically don't write it. And if there's nothing outside a set of parentheses, don't even write the parentheses. Similarly, AgBr. Ag is a +1 charge ion. Br is a -1 ion. You might write initially Ag1, Br1, but then just neaten it up to write AgBr. Lastly, is this equation balanced? So if it weren't, what we would do is write large coefficients in front of the compound's formula. But in this case, there's one lithium on the left side, one on the right. There's one nitrate ion on the left side, one on the right. There's one silver ion on the left side, one on the right. One bromine on the left side, one on the right. It already is balanced. So this equation is nice in that it's already balanced. Okay, great. We've written a balanced equation. Now, can you indicate whether it's aqueous or solid? AQ means it is dissolved. S means it's not dissolved. Well, students, initially, the reactants always have to be dissolved. They must be aqueous in order to get them to mix together. So without needing to think too hard, I'm going to put AQ in the parentheses behind each of the reactants. But for the products, we do need to consult our solubility rules. So we've got LiNO3 and AgBr. Let's go back to these rules and consider which one or ones might apply. Let's take LiNO3 first. I see rule 1, nitrate salts are soluble. I could stop reading right here because whatever rule is listed higher in this list would take precedence over anything listed below it. It turns out that rule 2 also would apply because lithium is a group 1 metal. In this example, both rules 1 and 2 reinforce each other. That would make lithium nitrate a soluble substance. We'll put the AQ there. Now let's consider AgBr. Let's go back to our rules. Okay, AgBr. Is there a nitrate ion in it? No. Is there a salt with a group 1 metal or ammonium ion? Well, check where Ag is. Is it in group 1? No. Is ammonium ion part of AgBr? No. So rule 2 does not apply. Rule 3, salts with chloride ion, bromide ion, yes, that would apply, or iodide ion are generally soluble. Now read to the end of the rule here, except when combined with Ag+, Pb2+, or Hg2+. Hey, students, we have one of the exceptions. So rule 3 applies, but it's one of the exceptions that makes this your solid precipitate. AgBr will be the solid precipitate in this example. Ooh, fun stuff. Good luck on the homework, students. Thank you.